to the next point. We should ensure whatever we see is clear.
That means work is being done. We can see that it is in opposite direction.
Good day, learners. You are welcome to part 4 of the topic waves. I'm looking at waves, part 4, on the subject physics. I remain Napoleon Kure. On the part 4, we are looking at stationary or standing waves. Before now, part 1 deals with introduction or some wave concepts, which we were able to look at forms of waves, types of waves, and classification of waves. Beyond that, we also have another way of categorizing waves, either as traveling waves or we call it progressive wave, which we have discussed so far. The other aspect of it is stationary or standing wave, which we are now dealing with. The second aspect we look at under waves, that is waves part 2, we look at mathematical relationship between wave speed, frequency, and wavelength. Then part 3, we look at mathematical representation of a progressive or traveling wave. For today, under part 4 on waves, we are looking at stationary or standing waves. What is a stationary wave? It simply means a wave that is formed when two progressive waves of equal frequency and amplitude traveling in opposite directions are combined, or they are superimposed, or they are overlapped. These are synonymous words that could be used. I take it again. A stationary or standing wave simply means a wave that is formed when two progressive waves of equal frequency and amplitude traveling in opposite directions are combined, are superimposed, or are overlapped. Most stationary or standing waves are obtained as a result of the combination or superposition of an incident wave and its reflected wave. What is a reflected wave? A reflected wave is of the same frequency and amplitude as the incident wave, but both waves, that is incident wave and reflected waves, are exactly out of phase. Under part 1, we discussed what we call in phase, when the crest of a wave and the crest of another wave are together, coincide, or the trough of the incident wave and the trough of another wave also coincide. We refer to that as in phase. But when the trough of an incident wave coincide with the crest of another wave, we say they are out of phase. The crest of the incident wave, as we said, coincides with the trough of the reflected wave, and vice versa. That is to say, incident wave, oncoming wave, and then the wave that is going back the opposite direction. When the crest of the incident wave coincide with the trough of the reflected wave, or when the trough of the incident wave coincide with the crest of the reflected wave, we say they are out of phase. And that's exactly what happened when stationary or standing wave is formed. The general shape of a stationary wave is shown below. Diagrammatical illustration of a stationary or standing wave. In the diagram, we can see a line. Normally, we have your horizontal line, which in this case is represented by a string. And we have vertical line. There you have a wave coming from the origin or the intersection of the vertical and horizontal as a source, and is going up. On reaching the maximum point, known as a point and maximum displacement, an antinode, it will come down to touch that horizontal line and go below it to another extreme point, and then go up again and in that form. And we call it incident wave. It is a thick line. On moving and reaching another point or a barrier or a reflector, we see that a wave will now move in the opposite direction to the incident wave. And that wave is referred to as a reflected wave. We can see that it's a broken line. So, on it, you can see the incident wave, as can be seen with an arrow, reflected wave. And between the point where the wave is generated, that is the intersecting point of the vertical and the horizontal, which is a source, and the maximum point where the incident wave reach, capital A. Between those 2 points, we have what we call 1/4 lambda, lambda by 4. And the point of generation of the wave, of course, is our node, capital N. The points capital N refer to that. Now, between the point of generation of wave and another point where the displacement of the medium is 0 along the horizontal is another node, and it's lambda by 2, as you can see on the diagram. Between the same source and another antinode, the second antinode, we have 3/4 wavelength, 3/4 lambda. And in that order. Now, between 3 consecutive nodes, capital N, the first N, the second N, the third N, between them, you have a complete wavelength. By the time we've taken those 2 points, we have what we call a complete wavelength. The source of wave is where the intersecting of the Y and the horizontal are. So we have this as a general shape of a stationary wave. The points marked N, as I said, are called nodes. Nodes of the stationary wave. We call them node. What is a node? A node is a point on the stationary wave where there is no movement of the medium. That is, the medium is at 0 level. On the other hand, we have points marked A and are called antinode. Like anti means opposite, the opposite of node. And that point, an antinode, is a point of a stationary wave where there is maximum displacement of the medium. We can say not a point on a stationary wave where there is no displacement of the medium or minimum displacement of the medium. And antinode, the opposite, is a point on the stationary wave where there is maximum displacement of the medium. Capital A for antinode, capital N for node. Both longitudinal, as we've defined before now, and transverse waves can produce stationary waves. Reflecting back to our part 1 of the waves, we define what longitudinal and transitional. Both waves produce stationary wave. The vibrations of an air column of a tube can give rise to longitudinal stationary waves. Example, musical notes produced by wind instruments like flute, trumpet, or saxophone are due to longitudinal stationary waves. The grammatical illustration is as shown below. And this is a diagram reflecting what we refer to as stationary longitudinal wave in a pipe. We have the incident wave up there You can see arrow indicating the direction of the incident wave, and on going back, we have the reflected wave. Stationary waves can also result from vibrations of a plug string when both ends of the string are fixed. These are transverse stationary wave. The first one is longitudinal stationary wave. The second one is transverse stationary wave. Example of production of transverse stationary wave, music produced by string instruments. For example, guitar or piano result from the stationary waves of plug strings. Illustration by diagram also can be seen as follows. The diagram shows us a string fixed at both ends, and when it is plugged at the middle, we have what we call a loop that is formed. The incident wave goes towards the right, and going backward is a reflected wave. Fixed ends, incident wave, reflected wave. This is what we refer to as stationary wave along a string. For stationary wave, the following applies. The distance between a note, capital N, and the next antinode, capital A, that is NA, and vice versa. It could be between a node and an antinode, or an antinode and a node. The distance between them in terms of wavelength is equal to 1/4 wavelength, lambda by 4. On the other hand, distance between two successive, consecutive, that is one next to the other, nodes, capital N and capital N, or antinodes, capital A is equivalent to half a wavelength, lambda by 2. While distance between three successive nodes, capital N, capital N, capital N, 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 as we defined before now, or antinodes, AAA, is equivalent to 1 wavelength, lambda. Examples on application of how this is solved are follow. Number 1, the wavelength, lambda, of a stationary wave is 36 centimeters. What is the distance between a node and the next antinode? Solution. Wavelength lambda is equal to 36 centimeters given in the equation. Let the distance between a node and the next antinode be equal to L. But we've discussed this, and we've established the fact that between a node and an antinode, our L distance is lambda by 4, where the lambda is given as 36, and so L is equal to 36 over 4. Divide 36 by 4, it gives you 9. And therefore, our L, the distance between a node and the next antinode, is 9 centimeters. It is centimeter because the wavelength is given in centimeter. And so we make conversion from centimeter because your options, if it is objective, could be in either in centimeter, it could be meter, it could be millimeter, as is important. A centimeter is the same as 1 over 100 meter. So divide 9 by 100, it gives you 0.09 meter. Or in standard form, it's 9.0 times 10 to the power minus 2 meter. Or in millimeter, milli simply means 10 to the power minus 3, and is the same as saying 1 centimeter is equal to 10 millimeter. So multiply 9 by 10, it gives you 9 millimeter. So expression of your length, distance between node and antinode, could be in meter, in centimeter, or millimeter. Example 2. A wave of frequency 30 Hz forms a stationary wave pattern in a medium where the velocity is 13 centimeters per second. Calculate the distance between adjacent nodes. It's the same as saying consecutive or successive nodes, whichever one, adjacent nodes. Solution, frequency is 30 Hz, our velocity is 30 centimeters per second, and so the distance assumed is taken between the two adjacent nodes to be L. And we've also discussed this, that it is noteworthy of the fact that between a node and a node, or antinode and antinode, the distance between them in terms of wavelength is L equal to lambda by 2. What is lambda? We don't know. So from V equal to F lambda, the basic formula in wavelength or in waves, we have V is equal to F lambda. Making lambda the subject, it will be equal to V over F. Well, our V is a velocity or wave speed 30 centimeters per second divided by frequency 30. When it happens, you have lambda is 1 cm. And so the length between two adjacent nodes is equal to half centimeter. In fact, in decimal, is 0.5 cm, or 0.005 meter, or in standard form 5.0 times 10 to the power minus 3 meter, or 5 millimeter. Example 3. A stationary wave in a spring is fixed at both ends. If the frequency of the wave is 256 Hz, and the distance between adjacent nodes is 1.5 meter, calculate the speed of the wave. Solution. The frequency is given as 256 Hz. Distance between adjacent nodes, Nn, is L equal to 1.5 meter. Our V, the velocity we don't know, we put a question mark against it. But again, we have established that between two successive nodes, our distance, L, is lambda by 2. So our lambda, therefore, will be 2L, making it a subject. Our L is 1.5, substituting, you have lambda is equal to 2 times 1.5. And it will be lambda equals to 3 meter. From V equal to F lambda, our V will be equal to the frequency 256 multiplied by wavelength lambda 3, and then you have everything to be V equal to 768 meter per second. Example 4. For example 4, you have a diagram of, as we've discussed before now, under stationary or standing wave, we have longitudinal stationary wave and transverse stationary wave. A wave in a tube is an example of longitudinal, and we have that given. On the diagram, you have the antinode is marked S, X, letter X, while the node is marked capital Y. There are two antinodes there with two nodes. Where you have a barrier that is given is a closed pipe, please. It's a closed pipe because only one end is open. When it is two of the ends are open, we call it an open pipe. And so we have two nodes and two antinodes. The length between there will be capital L. For the longitudinal stationary wave, this diagram is given. We are to use the diagram above, which shows a stationary wave in a closed tube, to answer the following questions. A. Find the relationship between L, the length between of the tube, and the wavelength lambda of the stationary wave. B. Determine the distance between consecutive antinodes, XX, if the wavelength is 60 centimeters. C. Determine the distance between consecutive antinodes, between three consecutive antinodes, XXX, three consecutive antinodes. Solution. From the diagram, we see that our Y, we said, is our node, our X is antinode. But then the length of the tube, as I said, consists of two nodes and two antinodes. The distance between the first node and the antinode is XL, is XY, and is lambda by 4, plus the distance between the Y antinode, the next antinode. The second node and the next antinode, the second antinode, and it's still lambda by 4. So our L is equal to XY plus YX, which is equal to L equals to lambda by 4 plus lambda by 4. The LCM is taken to be 4. 4 into 4 is 1 times lambda is lambda, plus again 4 into 4 is 1 times lambda lambda. If you add lambda to lambda, because they have the same denominator, it will be 2 lambda by 4. 2 cancel with 4 to give you lambda equals to L equal to lambda by 2. So our wavelength relating with our length of the tube will be lambda equals to 2L, or we say L equals to lambda by 2. B. Lambda is 60 cm from the equation, and the distance between consecutive antinodes, L, is what we are asked to find. So from the formula relating the length of the tube and the wavelength L equals to lambda by 2, our L will be equal to 60 by 2, and that will imply L equals to 30 centimeter. C. We have to find the distance between 3 consecutive antinodes, XXX, and the distance between 3 consecutive antinodes will be L equals to unknown. Our L is equal to lambda. Again, we said before now, worthy of note to have this, that if you have antinode naught is lambda by 4 or not antinode. Not naught or antinode is lambda by 2. But if it is 3 consecutive node NNN, it will be exactly a wavelength lambda. Or 3 consecutive antinode AAA, it will be exactly a wavelength. With that, our L, the length of the tube, is equal to exactly a wavelength. And the wavelength we've defined to be 60 cm. And so our L is equal to 60 cm. With this, we come to the end. Once again, I remain Napoleon Kure. I invite my colleague, Buki Hassan, who will come to summarize what we've seen and then give you work to do. Once again, coronavirus is real. Keep learning as you stay safe and observe the rules governing it. Thank you till we meet in our next class. God bless you.
Good day, learners at home. My name is Hassan Buki. I believe you were able to follow what my colleague has delivered onto you. The lesson has been quite interesting. Before we finally end the lesson, I will want you to have it in mind that we said the region where you have maximum displacement of your wave along the along the vertical is where you have your antinode, and then the place where on the horizontal the displacement is 0, that is where we have the node. We go to assignment. Question number 1. Listen and listen carefully because I will take it gradually so that you can be able to follow and write it down. 1. Explain with the aid of diagrams the following. A. Stationary or standing waves. B. Longitudinal stationary waves. C. Transverse stationary waves. D. Node. E. Antinode. So the question expects you to explain all this with the aid of diagrams. Question number 2 says, radio waves emitted from an antenna are picked up by a radar after reflection from an aircraft in 4 × 10⁻³ seconds. How far is the aircraft from the antenna? Given that V, velocity, is equals to 3 × 10⁸ meters per second. Remember, the question is asking you how far. Okay? So, bear in mind, the question is asking you how far. Okay? How far is the aircraft from the antenna? That means distance. Is asking you of the distance. We have our references. 1, New School Physics by M.W. and Yakoha. 2, All-Inclusive Calculations in Physics by Solomon Dauda Yako. And 3, Senior Secondary School Physics by PN Okeke, and MW Anyakoha. Our contacts are Napoleon Kure, 080-3636-2105. I take it again. Napoleon Kure, 080-3636-2105. Then Hassan Buki, 080-6550-4346. Again, Hassan Buki, 080-6550-4346. Stay home, stay safe, and keep learning. See you in our next lesson. Thank you.